Hi, everyone. My name is Michael Zachman. I'm from Oak Ridge National Laboratory, and I work in the Center for Nanophase Material Sciences. I recently wrote an MRS bulletin article with my other co-authors that you can see listed here. And we were discussing how to use cryogenic techniques to access nanoscale structural and chemical information from solid-liquid interfaces, and specifically with the liquids intact. And so in this talk, what I'm going to be doing is kind of going over a couple of the examples from our paper. I chose basically to go over a couple specific examples rather than talking about general, how these could be used generally, because solid liquid interfaces are really important for a really broad number of different fields, such as biology with biomineralization or chemistry, energy storage, corrosion. But rather than going over all of that, I'm just going to generally tell you how the techniques work and then how I used them specifically. In my experience, my PhD at Cornell was all in these cryogenic techniques for energy storage materials. And then I'm going to show you one that Danny Perea here, the last author, uses for atom probe tomography. He looked at some corrosion of materials. Okay, so the example that I want to talk about is lithium metal batteries, which basically are the next generation of batteries that will come after lithium ion batteries, hopefully. They have a higher energy density, but the problem is that they have some issues with depositing metals. So lithium-ion batteries have graphite anodes that store the lithium ions inside. Lithium metal batteries just use a chunk of lithium metal as the anode. And so this is what you see here. There's a liquid electrolyte and a solid lithium metal. And the problem comes when you try to deposit lithium during cycling of the battery. You get these dendritic structures rather than flat lithium. There are two main problems with this. These can break free, and then you lose a lot of your active materials, so your really high energy density battery drops in energy density rapidly. And then the other thing is that these can, maybe more dramatically, they can grow across and touch the other side of the battery, short circuit, and then catch the battery on fire or explode. So there are both longevity and safety issues associated with this. And these are tied intimately to breakdown of the electrolyte on the surface of the lithium. So the electrolyte breaks down and forms these solid and kind of soft materials at the interface here. And you can see that it's thought to be on the order of tens of nanometers in size, or maybe even smaller, but it has a lot of small components inside. So we're talking about nanoscale things here. And the inhomogeneity here is thought to be able to seed the dendrite growth. And so understanding this structure and chemistry at this nanoscale at the interface is very important for stopping these dendrites from growing. But the problem is, this is nanoscale and it's at a solid liquid interface, which presents a lot of problems. And so we need a really high resolution technique that can look at this with this whole interface intact. So I'll tell you about a couple techniques that we use that are very high resolution, and then how we can adapt those to use with cryogenic techniques. So the first is scanning transmission electron microscopy. This is what my experience is in. Here we have a focused electron probe that's focused to smaller than an atom. And we can get a couple of very useful signals out of this. So high angle scattering carries information about the nucleus. So you have atomic number contrast images that you can get out of this by integrating up this signal. You've probably seen HADF images in a lot of papers before. If you take the low angle scattered electrons, those are the ones that interacted with the electrons of the sample. And so they lose some energy, and every material has a different, or every element has a different characteristic energy that it loses, and you can integrate up that signal from those energy loss edges and get elemental maps like this at atomic resolution. But it actually carries more information than just that. Each edge has a fine structure to it that's associated with the local electronic environment. So the bonding environment of the materials, and you can actually resolve these also with atomic resolution. So you can pick out not only the elements, but also their local bonding environments. So this is going to be important for this battery work. The other technique that I'm going to talk about is atom probe tomography. This is what Danny is an expert in. And I have to say thank you for the intro slide to John Poplowski here at Oak Ridge. He's our local expert in this. But the way atom probe tomography works is that you make a sample into a very thin needle shape. You apply either a voltage pulse to it or a laser pulse, and that ejects atoms from the tip as ions. Those ions are accelerated to a detector, and if you know the voltage that you accelerated them with and how far away the detector is, you can measure the time that it took for them to get there, and you can get the mass to charge ratio. And so you can actually get sensitivity to different types of ions. And through this, they can reconstruct in 3D where each of these atoms came from in the sample with nanoscale precision. And this is what the final product looks like for that technique. So this, you can see grain boundaries and all types of things. So the idea would be to use this with cryogenic techniques to be able to see solid-liquid interfaces with nanoscale resolution in 3D. So there are a couple problems with this. Both of these are techniques that are done in a very high vacuum. So if we just look at a phase diagram for something general, like this is just a generic one for water. If we start at room temperature and pressure where it's a liquid, when you put many materials that are liquids at room temperature into the vacuum of the microscope, they would boil off immediately. So there are a couple ways that we can think to address this. One is that you could just encapsulate the liquids so that you stay up here in the room temperature and pressure roughly range. And this is called in situ. So basically you can, for example, in TEM, you can take membranes and encapsulate the area where the sample is so that you can hold the water or whatever other liquid you want in there, put the beam through it, and you can see your sample. So this is really useful for looking at small samples that fit between the windows. You can look at nanoparticles or other things, and its real strength lies in that you can look at dynamic processes this way, because this is sitting in the liquid. You can apply a bias to things, and so these are actually lithium dendrites growing on the edge of an anode here. So it's really good for looking at dynamic processes, and you can look at things with a pretty good resolution because you're looking at them in the electron microscope. But the thickness of the cell does limit resolution somewhat, and especially the spectroscopic capabilities of the technique. So, and it's also limited in sample size because you have to fit it between the windows. So we wanted to come up with a complementary technique that could maybe have thinner samples to let us get better resolution and to also let us do spectroscopy on the samples more easily. And so the other option, instead of encapsulating the liquid, is immobilizing it. So if you rapidly freeze a liquid, it will turn into an amorphous solid that captures nearly its native state. And then when you put this into the vacuum of the microscope, it stays frozen, and you have a solid version of your liquid that you had before. This is nothing new in principle. This has been around since the 80s in biology. So here they have some bacteriophages in the 80s looking at, this is amorphous ice around it. And this has come a long way. You're probably aware that it won the Nobel Prize recently for single particle techniques. And this is one of my favorite examples because you can actually resolve a water molecule bonded to this structure here. The limitation here, though, is that these have to be in very thin frozen solutions. So they directly freeze these tiny little molecules into a thin aqueous solution. And by doing this, you can get atomic resolution, or nearly atomic resolution, through the structure. The problem for us, however, if you remember, we're interested in these things that are very small, nanoscale, but they are within macroscopic devices or bulk samples, so they usually come in large things. I mean, this is something that you would put into your device. And so there are nanoscale features inside of here that we want. We can't just directly look at it. So this is where the technique that we use to prepare samples come in. It's focused ion beam, and it's a very versatile tool because it has an electron column for imaging, and then it has a gallium ion beam that can be focused to mill away materials so that we can mill away material inside of here to reveal what we're interested in. So what we need to do in order to accomplish cryogenic techniques inside of the focused ion beam is replace the stage with a cryogenic stage. So this is a cryogenic stage cooled by cold nitrogen gas that flows through here. And then you put a ceramic plate between the stage and the rest of the fib to isolate it thermally. The sample slides into a slot here on the shuttle. And then we also have an anti-contamination device because when things are cold in the vacuum, all the materials floating around in the vacuum absorb to the surface. So we put this anti-contamination device directly above the sample, and it hopefully preferentially attracts things. And it's also cooled by these nitrogen lines. And just by doing this, you immediately get some capabilities for doing characterization of these interfaces in the fib. So this is a solid liquid interface from a lithium electrolyte material in the fib. So we can mill to expose this surface and then image, and you can see we have pretty good resolution even within the fib. And you can also do spectroscopy. So in this case, this is energy dispersive X-ray spectroscopy. Again, now this is an aqueous solution oxide interface. But you can see in this device, we can actually mill through, reveal this surface, and then do EDX spectroscopy on the surface and get nanoscale type resolutions here. But we'd really like to go even further. You know, we wanted to see the details within these types of layers on here. And so for that, we need STEM or atom probe. And to do that, we need a lift out technique, we call it, which is basically you find an area on your sample where you are interested in some feature. You use the ion beam to mill away the material on either side, leaving a vertical cross-sectional lamella of that. We use a needle to extract it from the sample. We cut it free, take this over and attach it to a TEM or atom probe post. And then we remove the needle and thin this down to electron transparency in the case of electron microscope samples, or about 100 nanometers across, I believe, for atom probe samples. And this is a very common technique with room temperature materials. It's done all the time. But there are a couple of major problems with that. One is pretty obvious. The needle is at room temperature with standard techniques. You touch the room temperature needle to your sample and it will immediately melt if it has liquids. So we need to have a cooled needle. And the other one is a little more subtle, but it is actually a bigger problem. And that is that at room temperature, you can use a precursor gas that has platinum or some other metal in it and use the beam to crack the organic off and leave behind the metal, which welds the tip to your sample. This is how we attach it to move it around. At cryogenic temperatures, however, that precursor gas sticks to everything and forms a micron thick layer. So for example, with batteries, it's a really bad thing because we have carbon in the precursor gas and we want to characterize carbon in our sample. And there's platinum in that, and that interferes with the HEDF imaging since it's a very heavy element. So we want to avoid that. So how do we get around these things? Well, the first, like I said, is fairly obvious. We have to have a cooled needle. So this has a very similar design to the stage where there's a ceramic section which insulates the tip of it from the rest of the shaft. We have the needle here on the end, and there's a copper braid that, if you look here, this is the needle. The copper braid runs and attaches to our anti-contaminator. So it gets its cooling through the anti-contaminator. I can see here it's positioned above the stage so that we can work on samples and lift them out. Now, to actually attach the needle, we use what's called a selective carbon mill, which is water vapor. And it deposits water vapor on the surface, and it still deposits all over the surface of the sample. So it's not a controlled deposition in the spatial sense, but it doesn't contain any carbon, so for our purposes that's very important, and doesn't contain any heavy materials, so it doesn't interfere with imaging if there are any little remnant pieces left over. So let's look at an example of how this actually works. So these are SEM images from in the fib. Basically here we've milled 2 trenches, and then you make what we call a J-cut, where you almost free the material with the ion beam, bring in the needle. And now I'm going to show you the water deposition. This is now looking down from the top. So the needle is on the left here, and this is the lamella. And I'm going to go back and forth a couple times so that you can see this, but this is the water deposition. So in this case, we have, looks like probably less than a micron, which is a fairly light deposition of water. But what this does is it attaches the needle to the sample, and then we come over and we use the ion beam to cut this last little section free, and we can lift it up and out. Now this is on a TEM grid, we attach it, and we use the water vapor again to attach, and then cut free the needle. And then from this point, we thin down to electron transparency. Okay, so coming back to the battery example. What we did was we took a coin cell battery, just like I showed the picture of before, and it has a lithium metal anode. We deposit lithium metal on there. We opened up the battery after we did this and immediately froze the part that had the electrolyte left over. And so what you get is this is frozen electrolyte over the surface of the battery, and wherever one of these dendrites was growing, the electrolyte was raised up a bit because of surface tension. So within these, you can mill into them and reveal what's inside. So this is one of the dendrites. It's embedded in an electrolyte above lithium electrode. And we did use a platinum layer on top just to protect before we started any of this. And then I'm not going to show you all the steps again, but this is the final product. So this is lifted out, attached to a TEM grid, and thinned down to electron transparency. So this will be the sample that we then transport to the cryostem. So we transfer it on a cryotransfer holder underneath the liquid nitrogen so that it stays frozen and clean the whole time. And once we get into the microscope, this is electron energy loss spectroscopy mapping of this dendrite electrolyte interface. And we learned a couple things from this that came from not doing standard preparation. I should mention that the standard preparation for this type of sample would be to wash off the electrolyte and then dry it out and look at it. And so in this case, we left it intact, and because of that, we can see right away that this is much thicker than the 10 nanometers or so that we normally associate these solid electrolyte interface layers with. It was closer to 400 or 500 nanometers thick. And the other thing that you may or may not be able to tell from this is that the oxygen content was a lot higher in the SEI than in the electrolyte material. And we also found this these interesting fluorine-rich structures near the SEI. So like I mentioned before, you can not only just map where the elements are, but you can look at the fine structure, which reveals the bonding environment. So for example, we're looking at carbon here. So this is the carbon-oxygen double bond, carbon-hydrogen, and carbon-carbon double bond. And you can see the magenta curve has a much higher carbon-oxygen double bond content. So we can see not only is it just carbon and oxygen with a higher oxygen content in the SEI, it has carbon-oxygen double bonds. And so what we think is going on is that the electrolyte is breaking down on the surface to form this lithium ethylene dicarbonate, which does have a higher oxygen content and carbon-oxygen double bond percentage, and it produces this ethylene carbonate as ethylene as a byproduct, which can then react with the fluorine to cause these big structures. Okay, so through the cryofib preparation, cryostem, we can get really high resolution in 2D, but now I want to talk about preparation for atom probe, where we can get 3D information. So atom probe presents an additional problem for preparing these samples because the forces that it experiences through these pulses of voltage and the accelerating voltage off of it are very high, and so you need to more securely attach it to the post than we have to do for electron microscopy. And so what Danny and his collaborators figured out that they could do was when they put this onto the post, you can mill these little cuts in them. They call them little redeposition cuts, because what happens is some of this material is sputtered nearby and it attaches this more strongly than just a standard GIS deposition. But then in addition, they make a cut on the side and deposit an additional material with the GIS. So this enables it to have a really strong connection that can withstand the forces in the atom probe. Okay, so I'm going to show you an example of the lift out and some results that he got. So this is basically the same type of lamella that we would make for TEM. He's put it on the end of this micropost and made these cuts. And then you cut it free right here, and you can extract this part. You can actually make multiple posts from this. And now this is the atom probe lift out specimen, and they would thin this down to a needle type shape. So this is an image of what's within the sample before it's thinned down. So you can see there's a glass water interface. What they're interested in is the corrosion of this surface. So they're looking at the interface between a glass and a water, and there's a corrosion layer similar to the breakdown layer that we looked at in the battery. And this is the final thinned down product. So they made a needle that you can see ends up a couple hundred nanometers across at the top. You transfer this over to the atom probe, and you can do the same type of analysis that I showed in the intro slides. And what they found was above the corroded glass, there are actually alkali poor regions and alkali rich regions. And you can see nice 3D nanoscale type resolution of where all these different materials are. And you can draw line profiles across, for example, one of these alkali rich to poor boundaries here. You can see that the lithium and sodium content goes up significantly in the alkali rich section. So we can use cryofib lift out techniques to prepare samples in slightly different ways for TEM and for atom probe. And then with TEM we can get, I mean, in theory you can get down to atomic resolution if you have a material that can withstand it in the TEM. And then in atom probe we can look at the nanoscale distribution of all of the elements inside, but in 3D, so we can get a nice 3D structure from the two. Okay, so with that I just want to briefly wrap up. We've looked at the beginning, we looked at you can image dynamic processes in situ electron microscopy, which is really useful for watching things happen in real time. But some of the resolution and the size of the sample is limited, so a complementary technique is cryo, where you can look at small features within large samples, and you can do so at high resolution. And using the cryofib, you can prepare samples both for cryostem and for cryo APT. And then using those techniques, you can get nanoscale or possibly atomic resolution, structural and elemental and bonding environment information from CryoStem, and nice elemental concentrations in 3D with Atom Probe. So thank you very much, and I think we have a question and answer session now.
Well, Michael, thank you for that excellent talk. I mean, you're really some very beautiful work and extremely challenging work that you've been sharing with us there. There are a number of questions come in, and some have obviously some overlap between them, but I think one of the first questions that people want to know is how beam sensitive are battery materials when you're working at cryogenic temperatures?
All right. Well, first, thank you. That was very nice of you to say. So beam damage in battery materials is actually very important. It's just like in biological materials, they tend to be very sensitive, but it tends to be more of the liquid side of things that are very sensitive. So for example, the liquids that they used, they were carbonate electrolytes, and they tended to damage around 100 electrons per square angstrom or so, or even below that. But what we found was that there were different damage mechanisms that occurred at different doses. So at that sort of very low dose, you would start to get some very small bubbles that were probably hydrogen coming off of the molecule. So if you're interested in large structure of the materials, like I say large, but on the order of hundreds of nanometers or something, that would already be disrupting it at just 100 electrons per square angstrom. What we were more interested in was the fine structure, and specifically the fine structure of those carbonates. And that tended to be much more resilient under the beam. I mean, it was still very sensitive compared to traditional hard materials, but that would go up to more like, 10 to the 3, 10 to the 4, something like that before it started to damage. So that type of, the electrolyte side is pretty sensitive, but if you look at the lithium side, there were different materials that we looked at. So lithium oxides, lithium hydroxides, lithium hydrides, and lithium metal itself. Those tended to be higher, at least 10 to the 4, 10 to the 5, usually before they start to damage. And I'll just mention one thing that we found that was really interesting was if you have lithium hydroxide or peroxide or something, what it does is it converts to lithium oxide. And then after that, basically lithium oxide is stable and you just get mass loss over time. So if any of you are looking at lithium materials, just know that if you're looking at lithium hydroxide or peroxide, it could potentially change to something else under the beam. But lithium hydride and lithium are actually pretty stable under the beam at cryogenic temperatures, and so those can go up to 10 to the 5 or more before they really start losing much mass. They don't ever change their bonding structure, really.
Right. So what would you say currently is the biggest limiting factor for analyzing samples by cryofib lift-out and cryostem?
Mm-hmm. That's a good question. So these are all very early techniques. Only a few people are doing it so far, and so there are a lot of things left, but I think probably one of the biggest limiting factors once you get over the human experience of doing it, you have to get good at it, which takes quite a while. Once that's not the limiting factor anymore, the limiting factor is probably contamination, I would say. So you may have noticed on even some of my samples that I had there in the paper that there are small pieces of ice. This is because at different stages in the transfer or in the storage, you can end up with that sort of thing being introduced. Even if you do everything properly, there's still moisture in the air. And so you can end up with some possibility of getting ice on your sample. So first, I think things could be more user-friendly eventually, and that might help with this initial getting up to speed with everything, which takes quite a while. But once you are there, we still need to make improvements in transfers between instruments and clean nitrogen to store in, because you can go through an entire day of preparing one of these samples, store it, and then get it to the microscope, and then find out that the 10 nanometer thing that you're interested in has a 1 micron piece of ice on top of it, and you did everything right, but it's just too bad. So I think that's the biggest thing, is that you can just be unlucky still with contamination.
Yeah, so there's still a lot of room for improvement in terms of both equipment and the workflow to be developed. Yeah, absolutely.
I think so. Yeah, I think it'll still come a long way.
Yeah. And so there's a couple of participants are asking about when you're doing the fib prep. Again, it's really a damage related question, but what's the impact of the scattering of the ions? Does it cause local heating? Does that result in decompositions in the liquid electrolyte?
Right.
Any comment on that? Yeah.
So as far as heating goes, because you have a big bulk sample and you're not putting that much energy in the fib, with the electron beam, I should specify, it doesn't cause that much local heating, so that's okay. If you use a really low voltage, you can deposit all of the beam energy into a very thin sample, and that could be a problem. But when you're using a high energy, for example, in the microscope, when you're using a high energy and most of the energy passes right through the sample, you're not depositing all that. So heating is not that dramatic. But the ion beam damage question, that is a very important one, and especially for these beam-sensitive materials. I also think that it's something that's not very well explored yet because it's more difficult. So in our study, basically by the time they got to the microscope, it looked like something similar to that very initial, like less than 100 electrons per square angstrom type of structural stuff could have happened. But again, it's difficult to say exactly because you can't go to see what's happened to your sample without looking at it, which for a really sensitive material, you already have the potential for introducing that. So I think honestly that is something that really still needs to be looked into probably. If people really get into doing this, I think that more in-depth studies on ion damage probably to frozen like carbonates or just generally organics should be looked at. So the thing that I will say is that if you use a low ion energy, you can run simulations in something similar to the material you're looking at and see how deep they penetrate. And cryogenic lift-out samples, because they're so soft materials, they tend to be thicker in the end than a nice room temperature hard material would be. So if you're operating in a range where, say, your ions may go in 20 nanometers or something, and then your lamella is 100 or 150 nanometers thick, you still have a pretty large section that could be undamaged. But again, this is all material dependent, and I can't tell you ahead of time. I couldn't predict what type of damage would happen for any particular material, just what we've seen.
Right. And then I guess, again, there's a couple of different questions relating to the temperatures that can be achieved and the variability or the ability to vary the temperature. So what in cryo, I guess this specifically in cryo-TEM, so what is the lowest stable temperature which can be achieved cryo-TEM? And, we can discuss what we mean by stable, when you achieve that temperature, can you control and vary the temperature during imaging so that you might study, for example, phase transitions at low temperatures? Right.
Yeah, so, you hit on it. The stable word is the key one there because we can technically go all the way down to liquid helium temperature. All you need is a dewar that you can put liquid helium in, a holder that has a dewar for that. So right now, I would say the lowest that you can do stable enough to work basically how you would at room temperature without major changes is liquid nitrogen temperature, and you can get within 10 or so degrees of it or something with these standard cryo holders. There are some techniques that are needed because it still isn't as stable as you are at room temperature. There's large scale drift just kind of in a constant direction from the expansion or contraction of the rod, depending on how much nitrogen is in your dewar. Small bubbling in the dewar can cause vibrations. So there are still challenges even at just a standard temperature like liquid nitrogen. But you can envision, and some people have done a few experiments already with cryo holders that can go all the way to liquid nitrogen or liquid helium temperatures. The problem is that one is liquid helium boils off a lot faster than liquid nitrogen, so you're working on a lot shorter time scale. So normally we wait for quite a while for stability to happen once the dewar is filled with nitrogen. That's a lot harder with helium. And because it's bubbling a lot more, those small vibrations are also a lot worse. So a real true liquid helium temperature, I think, will take a more integrated design of the stage rather than just one of these side entry holders. But currently, I would say liquid nitrogen temperature is pretty reliable. And in the future, hopefully, we'll have more instrumentation for liquid helium temperature to improve.
Okay. There's questions come in about some of the results that you're actually showing. specifically, are the black spots in the SEI evidence of porosity in the SEI, or are they artifacts associated with the preparation?
Yes, that's a good question. So those are very significantly different from any of the little bubbles that we get from either preparation or exposure to the beam. So what we think is that those are actually bubbles in the SEI. And if you remember the reaction that I showed that's consistent with our EELS data, it was going from the ethylene carbonate in the electrolyte to a lithium ethylene dicarbonate. And the byproduct of that is ethylene gas. And so right on the surface of the lithium, you'd be producing ethylene gas, and some of that would become trapped in the SEI potentially and leave these bubbles. And then also some of it's floating around in the SEI. There's an old theory paper that shows that that should be able to bond to lithium fluoride. And we kept finding these large large fluorine-rich chunks. And so that kind of supports also that they're forming this kind of composite material with the ethylene and the fluorine chunks. But yes, we think they're bubbles basically from the decomposition, not from the beam.
And then, well, first of all, someone's just confirming that you're using water instead of platinum in order to weld the sample onto the needle, which I think you explained carefully that's what you were doing. But someone's also asking, just confirming that you were using a gallium fib. But we might broaden that question out a little bit and ask, is a gallium fib the best tool to use this? Would a different plasma fib or something like that be a better choice? So,
yes, we were using a gallium fib, and I do think that it is not ideal, honestly, because while you're at cryogenic temperatures and you can get a much lower reaction rate with gallium, which sometimes can interact with materials, especially with lithium. Lithium can be really bad. It basically stops that, but you can still get gallium implantation. And we would often find these gallium-rich sections at the very bottom of the lamella kind of hanging off. So if by chance you're interested in something down there, it could interfere. So to avoid that kind of thing, I think that going to a plasma fib would be very useful. And then I didn't show much of it in my talk, but the other side of this that we found from a practical perspective, working with the battery folks, they were really, really often interested in using the fib itself to mill in and to look at interfaces within the devices that they were making. And in that case, I think a plasma fib actually has some pretty big advantages because you can mill much larger regions much quicker. And so I think maybe on that side, it's even more useful eventually.
Yeah, and I mean, it's also interesting, with the capabilities, the imaging capabilities in the fib these days, ability to do, STEM imaging in a fib. There'll be some cases here where it's almost better to do the entire experiment inside the fib rather than even taking it to the TEM.
Yeah, absolutely. It depends. It just depends on how small you need to see and if you need bonding information, because you can get some elemental information at a pretty decent resolution from within the fib. You again have to worry about beam damage, and it's actually, I think, from my experience, it's a little harder to diagnose when your damage starts to happen because you can't look at that fine structure. You have to basically rely on structural changes and mass loss, which can be, that's not the onset from what we've seen of damage. But you can, in principle, you could do a lot of this stuff down to at least 100 nanometer type resolution, and we've gone down to maybe 10 nanometers or so if you have the right materials. So you can do a lot in the fib, and I think that's where a plasma fib actually would be useful to expose new things and more of them than we can right now.
Yeah. We'd look for more instrumentation development, I think, in that area. I think you touched on this, but maybe they just need to reiterate again. Is someone's asking you, how do you transfer the frozen samples from the cryo fib to either the STEM or to the atom probe?
Good question, because something I didn't get a chance to explain really. Yeah. On the instrument side, all of these techniques, for example, I guess old school biological before they had their new microscopes with integrated holders for this, but biological stuff a while ago, material set like the type of stuff that John was talking about where you directly freeze samples. If you're doing that type of thing, you can freeze your sample directly onto the grid And then all you need is somewhere to keep that sample underneath liquid nitrogen, and you can use a standard cryo holder, for example, from Gatan. And these are they're very similar to a normal side entry holder, but they have a big liquid nitrogen dewar on the side. And then on the tip, they have a little device that slides over the area where you put the sample that's supposed to help with that contamination issue that I was talking about when you transfer. So what you do is you start with your sample in a little nitrogen pot. You put the tip of the holder in there underneath of the nitrogen, and you put your sample into the tip and secure it, and then you slide this little shield over top. And then this is where besides that, that's actually very difficult to do. That's where personal experience comes in too. But getting it into the microscope quickly is then very important because you have to come out of the nitrogen and then into the load lock of microscope. And so the more quickly and smoothly you can do that, the less risk of contamination on your sample. But for example, that's one of the areas I think could be improved at some point, was a better way of protecting that sample between there. But right now you just pull it out of the nitrogen and put it into the load lock quickly. But if you have to include fib preparation, like what I did and what I showed, you freeze your sample and put it into the fib. And we had a load lock. We used a quorum load lock. And you put that in through vacuum system into the chamber of the fib, and then prepare it. And on the way out, there's a little vacuum transfer device that goes from the preparation chamber on the fib to a nitrogen pot. So it's kind of the reverse of putting it into the microscope. You come out in a vacuum device, which is better than just the shield. And then you put it into the nitrogen. There's a split second between opening up that vacuum and into the nitrogen that you could potentially have some more contamination, but that's supposed to be a more nitrogen environment, so hopefully not. You go into the nitrogen pot, and then from there you can just store it in nitrogen until you end up at the same point that you would to load it into the microscope with the other samples. So it's kind of a three-step process of making it, getting it out of the fib, and storing it, and then moving it to the microscope.
Can I add there that there's actually a lot of efforts from companies like Leica, and you mentioned Quorum, focused on that transfer step and keeping that transfer step completely under LN2 and away from ambient conditions. So that's very encouraging, I think, for the workflow that there's companies targeting that specific action.
Yep, I think whoever gets a really good transfer first too will probably benefit a lot from it, because I think that's one of the last things really.
Yeah, I think that's one, as we were saying earlier, I think that's one of the areas where there's still room to improve the instrumentation to make that workflow much more reliable.
Yep, I agree.
Yeah. Someone's going back to your answer regarding the damage in the gallium fib. So related to that, they've asked, is there any strain induced by the fib? You're actually milling the specimen.
This person must have worked on some things before. Yes, actually, in a lot of materials in the fib, as you get very, very, very thin, you can start to get some bending. So, yes, and so if you're looking at, if you want to see what the crystalline structure of the material is, I actually don't know the implications of that because we weren't interested so much in that. But yes, I would say if you are working with a fib, that's something that you need to be careful about because you can see bending of your sample a little bit once you get down to these very thin lamellas. So any crystalline material, if that's what you're interested in, you should be careful about that.
Yeah. On a much more general point, so someone's asked is, where can folks access cryofib at the moment? And so I could make a plug for my own facility here at the Ohio State University. We have a cryofib here, and we're a user facility, and people are welcome to approach us. I don't know whether in the national labs and the nano centers there are cryofibs available. Can you or John comment?
Yeah, so at the Center for Integrated Nanotechnologies, you can find the capability at cint.lanl.gov. We have a cryofib that is operational and a cryo-TM and transfer equipment.
There we go.
I'm glad you guys can speak up. So there is also one at Cornell, obviously, since that's where I was.
Yep.
And I talk to people at conferences, and I know who's planning to get them, but I don't know what stage they're at. So I'm glad you guys can speak to where there actually are some at this point.
Again, there's a question that coming back to the black spots and the SEI. Now, let me read the question explicitly. It says, compared to the black spots in SEI, have you also observed some defects, artifacts in the SEI layer? Are they also related to bubbles?
let's see here, in the SEI layer. I guess I'm a little confused since those are in the SEI layer.
Yeah, I was slightly confused by that question.
Yeah. Yeah, so there are some, I mean, maybe they're talking about this, the fib image of the lamella versus the eels image. So there are some larger ones that you can see in the fib, and those, I think basically they are all bubbles all the way around. Some of them are larger, but some of them look less dark in the fib because they're not cut on both sides, so they're not showing vacuum behind it in the SEM image. But we still see through those in STEM because the electrons pass all the way through, and the material's thinner, so they can still show up dark. So some of them we don't see as well in the fib, but they do show up in the STEM more clearly. I don't know for sure if that's what they're saying, but maybe. Okay.
And then again, there's a battery chemistry question. Do you expect the LiPF6 to remain retain its structure while dissolved in the electrolyte at room temperature, or once it's dissolved, does it already decompose into lithium fluoride or other binaries? So
I definitely am not an expert in this, but there are papers on this on kind of the percent that you expect these to break down. For example, into lithium fluoride specifically, I know some of the lithium PF6 breaks down into lithium fluorides. There are little small trace amounts of lithium fluoride floating around. I'm not sure I've seen lithium hydride or lithium oxide, but lithium fluoride for sure. So you should be able to look up papers. I think they have quite a few of those that talk about breakdown of that molecule in the electrolyte.
Okay. And then sticking with chemistry for the last question is, someone's asked, doesn't lithium react with nitrogen? And how do you avoid issues with that?
I have to say, we worked with Lyndon Archer's group at Cornell, and this was the very first question he asked us. Because it's a very good question, a very important question. So what we found was that, no, it doesn't actually. If you freeze it fast enough, that prevents any reaction. We didn't find any nitride on the surface of it, which was actually a little surprising to us. So just the drop in temperature, the rapid drop in temperature, it didn't. The concern was that lithium can interact with nitrogen, which if you leave it out in the air, you'll see that. And that we have very, very concentrated nitrogen, and so that could potentially lead to a very quick reaction, potentially violent reaction. But what we ended up finding in our experiments was that it didn't. So that's a very good and important question, and I'm glad you asked, because that would be kind of terrible for all of this if that had to happen.
Well, I mean, I think there was a terrific number of questions that came through for both of our speakers there, and we've finished almost exactly on time. We've just slightly running over now. So I guess at this point, I'd like to thank both John and Michael for really wonderful talks. The comments in the chat room are highly complimentary on all of the presentations, and I would like just thank everyone for joining into the webinar and showing such interest in what we think is a really topical area and an exciting area of development of cryogenic electron microscopy and material science.